Okay, so let's see here. So obviously, I first just a couple notes. So I know some of you are concerned regarding the assignment sheet and the upcoming test. Obviously, some of those things are being delayed. I'm gonna please keep track of Google Classroom. I'd like to post on Google Classroom. I'd like to post a new assignment sheet so you guys are better informed as to when things are due. Obviously, we are not doing the test for the currently scheduled date. I will post a new assignment sheet on Google Classroom, so please keep track of that. That being said, what we're going to do today is I wanted to go through the 1.5 lessons. So let's just before we do, let's just talk about a few things. So regarding lesson 1.4, there was one big idea that I did not teach. It's the intermediate value theorem. And I don't want to teach that one over video. I feel that we would do a better job, right? It would be better for you guys in terms of your understanding if that was taught in person. 1.5 though, I think is pretty straightforward, and I should be able to teach it, not an issue. So that being said, let's start on 1.5. Okay. Before we do, again, I should be back. I'm planning on being back hopefully Monday. That's the goal. It might have to be Tuesday, but I think Monday is when I should be able to be back. So the plan really is on, and I'll put on the assignment sheet like I said before, but the plan is that on Monday we go over the 1.4, the intermediate value theorem. I kind of go through questions that you have in regards to the reviews you've been doing, things like that. Just we're going to spend an extra day or two just catching up again, maybe go through a whole separate review so that you guys get a nice, good review with me in the class and things like that, and then we'll take our test. Okay? So again, I will be posting the assignment sheet. I know I'm repeating myself, but I know that's a stressor for you guys. Okay, that being said, let's see what we got going on here. So we've got a warm-up here. As you guys can see, what I'd suggest doing is pausing the video right now, doing the warm-up, and then we'll go over it. Okay, so I'm going to assume that you have paused it and taken whatever time that you need. Let's go over this. Let's see what we got here. So let's choose a good color. So on the first one, what do we got? We're going to be approaching the number -2 from the right? So we are approaching -2 from the right. I think you guys would agree that is a height of 3. So that limit equals 3. Okay, let's approach -2 from the left. And I think you guys would agree it is going to 1. In this case, now they're asking for this last question, what is the limit as x approaches -2? I think you guys would agree 3 does not equal 1. Left-hand side limit does not equal right-hand side limit. So my conclusion is does not exist. Okay, let's move on to the second one. So this next one is asking, is the function continuous at x equals 2? Obviously, it should say, is the function continuous at x equals -2? That is a mistake. Okay, so if you took it at x equals 2, could you fix that right now? So pause the video and fix that to going to x equals -2. Because at x equals 2, it actually, right? So just to be clear, because I gave it, if x equals 2, that would work out perfectly. So I could plug 2 into this thing. I'd get 0, right? Because 2 squared minus 4 is 0 over 4. So this would be 0, and it would be 0. So that would be fine. Everything would work out. This wouldn't even be involved in the whole situation. So at x equals 2, it was fine, but the more complicated question was x equals -2. So let's look at what happens when x equals -2 for this function. So the first thing I want to do, right, I'm just going to kind of go through my formula, my definition. I'm going to say, what is f of negative 2? And I think you guys would agree, f of negative 2, when x equals negative 2, the output is negative 4. So the function is defined at that value. That's good. Now we want to check it. What is the limit as x approaches, what was it? Negative 2 of the function. So in this case, I think you guys would agree, what I'm really going to be looking at is I'm going to be looking at this piece, because I'm looking at what's happening to the left and what's happening to the right. So that's going to be, this limit is going to be equal to the limit of that top part. So let's go and take the limit of that top part. So I'm going to factor the numerator. The numerator becomes x plus 2 over x minus 2. And what do we got here? Sorry, I was just checking my recordings to make sure the audio was actually recording, because if it wasn't, I would have been sad. Okay, so the x plus 2's cancel out. And so our similar function is going to be the limit as x approaches negative 2 of x minus 2, which equals negative 2 minus 2, which I'm going to simplify to negative 4. Okay, so the limit exists, and I think you guys would agree the limit of the function as it approaches negative 2 is that number we just found, negative 4. So finally, we want to check, does the limit as x approaches negative 2 of the function equal f of negative 2? And the answer is yes, it does, right? F of negative 2 was negative 4. The limit was negative 4, so they both equal negative 4, so this is true. So I'm going to make a conclusion, and this is important. Conclusion, let's see, f of x is continuous at x equals negative 2. Do make the conclusion. Don't stop right here after you've gone through, you found this. Don't just stop, right? Make your conclusion. I get a lot of people who just do all that hard work and then they don't finish up and say, hey, this is what I've concluded. Okay, that being said, let's continue. So today we're going to look at, and I want to emphasize this. So this says we are looking at properties of infinite limits. Okay, so we are looking at infinite limits. Now I'm going to stress this over and over and over again. A limit is where we take a function, right, and we are the output of a limit is a number. Okay, so when we're taking a limit, right, we're looking from the left and right, but what we're really saying is, what is the output of it? And is that output should be a number. It's not infinity. So when we say a limit is infinite, what we're really saying is this limit doesn't exist, and here's a description of what it is. It's infinite. Okay, it's going to negative infinity. It's going to positive infinity, but it is infinite. So one more time. An infinite limit is just a description of how a function fails to exist. A limit of a function fails to exist. Okay? Keep that in mind. So let's look what we got here. In this case, in the first one, what do we got? We got this function of f of x as it approaches this function, of this function. We want to know as x approaches 2, what is the limit? Well, I think you guys would agree, right? We've known this for quite a while. There's a vertical asymptote. It's unbounded. The limit doesn't exist. But now we're going to be a little descriptive, okay? So the first thing I'm going to do is I'm going to say, okay, well, what is it as it approaches 2 from the left? Well, as it approaches 2 from the left, it's negative infinity. So I'm going to say it's negative infinity, but I'm still going to put down here, because I want you guys to do this too, does not exist. So you're doing two things. You're saying, hey, the limit doesn't exist, and this is my description as to why. Okay? That being said, maybe pause the video right now and see about answering this question. Okay, I'm going to assume you've unpaused the video and you've done the work. So now let's see, we're approaching 2 from the right. Okay, so what's my conclusion? My conclusion is it's going to pos infinity, which again is a description of how the limit fails to exist at x equals 2. Okay, let's keep on going. Okay, so you should pause this right now, get down the stuff that you need, and then we're going to talk about it a little bit. Okay, so I'm going to assume that you have gotten down the things that you need. So while this looks bad, especially this, I want to kind of emphasize this is such a BC thing to say. I wouldn't get. Don't worry about it, okay? Here's what I want you to take from this. Okay, this is not a hard definition. Let's go back to the previous example. All it's saying is, okay, let's say x equals, we're looking at the limit as x approaches 2, right? It says as we approach either from the left or from the right, as we approach, let's just say from the left for now, as I approach this specific c value 2, for closer and closer values of 2, but not 2, right? If this thing is going infinitely down or infinitely up, right? That's an example of the limit failing to exist, but that's the limit. What we say is that limit is going to infinity. So in this case, right, this is saying in our case, as the limit as x approaches c, right, some c value, it's going to infinity. So as we get closer and closer to that value, right, in this case 2, if it's going up forever and ever or going down forever and ever, as in this case, then the limit is infinity or negative infinity, which one more time is a description of how it fails to exist. Okay? So, and I kind of put that down here. This was me being like extra. I want you guys to see this, right? This means it does not exist. Okay, so that is, I can't stress that enough. When you say a limit goes to infinity or negative infinity, you are describing how the limit fails to exist. That's probably the last time I'll say that. Who knows? Probably won't be. So, that being said, let's keep on going. So, let's see what we can do with these two. So let's look at this first one. In this first one, I think you guys would agree. Let's see. So our important number is at 1. So we're going to look at 1. So as I approach 1 from the left, it's going to pos infinity. As I approach 1 from the right, it's going to pos infinity. So what's my conclusion? My conclusion, let's just call that function, the first function, f of x. I'm going to call this one f of x, and I'll call this g of x. So I'm going to say the limit as x approaches 1 of f of x equals infinity does not exist, okay? So it is going to pos infinity. They're both going to pos infinity. So I can make an overall conclusion saying, hey, look, they're both going to pos infinity, therefore it does not exist. Now notice g of x. G of x is a little different. I can't just say it's going to infinity because this one's going to negative infinity. So if I wanted to, I could break this down a little bit. I could say, hey, look, the limit as x approaches 1 from the left of g of x equals negative infinity, and the limit as x approaches 1 from the right of g of x. Oops. Let's fix that. Okay? So I'm going to finish this one up, and then I'm going to clean that one up because I do see my mistake. Apparently, I don't know directions. So the limit as x approaches 1 from the right of g of x is going to negative infinity. Let's fix what I said above because I do see the mistake. Hopefully it didn't confuse any of you, right? As we're approaching from the left, it's going to pos infinity. Okay, I am going to make an overall conclusion. In this case, I can't say it's going to pos infinity. I can't go to say it's going to negative infinity. So I'm just going to say the limit does not exist. Okay, so I've done some descriptions here. Here's a description of how it fails to the, as I approach from the left. Here's a description of how it fails, as it approaches from the right. But overall, I can't make a single, it's going to infinity, it's going to negative infinity. So the best I can do is just say does not exist. Okay, let's move on. So I'll let you guys, again, once you pause the video, get down the definition of a vertical asymptote. So the nice thing about this is you guys have heard the word vertical asymptote a lot, right? This isn't something that you've been using vertical asymptotes for quite a while, but you never really got a precise definition. And again, the precise definition, right, is the function is hugging that vertical line, right? So that function is hugging that vertical line, and as the function gets closer and closer to that vertical line, it's either going to pos infinity or negative infinity. So that's a definition of a vertical asymptote. But now we have calculus to kind of talk about those limits and say, hey, look, that limit's going to pos infinity, that limit's going to negative infinity. Isn't that cool? Okay, so now we have a calculus definition, so we can actually give you a real definition of something that you've been using for a long time. So let's go find some vertical asymptotes. So quick reminder, vertical asymptotes occur when the denominator equals 0, as long as you're not it's not a removable discontinuity, right? So as long as there's not a hole or something like that. So in the first one, what I'm going to do is I'm going to look at letter A. I'll do it for you, and then I'll kind of give you guys some time. So for A, I'm going to notice that I think you guys would agree. I want to know, when does the denominator equal 0? Well, the denominator equals 0 when either 2 equals 0, which is of course not true, or when x plus 1 equals 0, so x equals negative 1. So I think you guys would agree, there is a vertical, and I'm going to do this abbreviation, there's a vertical asymptote at x equals negative 1. Not much to see with this. You guys did this for pre-calculus, right? So if you would please, could you finish up B and C? So pause video, do B and C. Okay, let's look at B and C. So for B, I'm going to factor. The numerator does not factor. I hope you didn't factor. That's x squared plus 1. That is definitely non-factorable. But the bottom, the denominator, can factor to x plus 1, x minus 1. There is no factoring from top and bottom I can do. I cannot cross off this and this. That's not allowed. I cannot cancel out a 0 from top and bottom. So what is my conclusion? My conclusion is that there are vertical asymptotes either at x equals positive 1 or x equals negative 1, right? X equals negative 1, x equals positive 1. So there's vertical asymptotes there. Let's label that. So vertical asymptotes at x equals 1, x equals negative 1. Let's do letter C. So in this case, I'm going to turn this into a fraction because cotangent x isn't giving me a lot of information. So this is cosine x over sine x. So I think you guys would agree. This has got vertical asymptotes whenever sine x, right? Whenever the denominator equals 0. And sine x equals 0 at multiples of pi, right? So at 0, pi, 2 pi, 3 pi. Is that right? Yes, that's right. Okay. Yes, just double checking. So in this case, if we were just looking at the open interval, if the question had been, hey, on the open interval from 0 to 2 pi, what's the vertical asymptotes? Well, you could say there's a vertical asymptote at x equals pi. In this case, they didn't restrict it that much. So what I'm going to say is I'm just going to assume it's all real numbers. So I'm going to say there's vertical asymptotes at n pi where n equals all the integers, right? So 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Okay? Okay, let's keep on going. Let's keep on going here. Let's look at this one. So we were going to determine all vertical asymptotes of this one. So stop the video, see what you can do. Okay, I'm going to catch up with you. So I am going to factor the numerator and the denominator. So the numerator becomes x plus 4, x minus 2. The denominator, difference of squares, so x plus 2, x minus 2. So this is important, right? And I know you guys know this. This is not a at x equals 2, there's not a vertical asymptote, right? No vertical asymptote at x equals 2. There's a hole there because there was a removable discontinuity. So the only place where there can be a vertical asymptote is when that equals 0. So there is a vertical asymptote at x equals negative 2. Okay? Let's keep on going. So we're going to go find the limits of these functions. So actually, why don't you, well, this is the same function. I want you guys to notice this. This is, we're looking at it from the left. We're looking at it from the right. So actually, I'm going to go through this one with you. I was going to have you kind of do it on your own, but I want to talk to you now about, okay, we've got a function that's a little bit different. It's definitely going to have an issue at 1 because I think you guys would agree there's going to be no way we can factor out x minus 1 from top and bottom. So there's absolutely an issue. So now the question becomes, you might know off bat what's going on with it, but how do I justify it? So we're going to have 2 ways of justifying this really when the limit fails to exist. One way is you could make a table just like we did in section 1.2. You can approach the function from the left, right? Approach it from the right. Right? We could approach it from the left, approach it from the right, and see what's going on there by using a table and then making a conclusion that way. Or you could just kind of sketch a little graph if you know what the graph looks like. That's what I'm going to do, okay? And again, please feel free to make a table, right? I can use numbers to the left of 1 here. This would give me this limit. I can use numbers to the right of 1 here. That would give me this limit. And I could find each of those limits and make an overall conclusion if I wanted to. But what I'm going to do instead, because I'm lazy and I don't want to make a table, is I'm going to just sketch a super inaccurate graph. So I am going to just take my function for a second. Let's just kind of put it off to the side over here. And I'm just going to factor it. So I'm just looking at the function itself. I'm not looking at its limit. I just want to look at its factored form. Okay, what do we notice? So if I were to just graph this, let's get some graph paper here. So if I were to graph this, and again, non-accurately, you and I already know there's vertical asymptotes at x equals 1. We've already seen that from the above examples that we did. So we know there's a vertical asymptote at 1. The only real question becomes at this point is at x equals 1, what's going on, right? As I approach from the left, is it going to positive infinity or negative infinity? As I approach from the right, same thing. So let's see what we can do. Let's see if I can put this together easily. And again, if you don't like what I'm doing here, make a table, okay? I have a feeling most of you would probably prefer a table. Again, I'm being lazy here. So let's see. I've got my vertical asymptote at x equals 1. I also notice, right, when this numerator equals 0, that's where there's x-intercepts, where it crosses the x-axis. So there are x-intercepts here at x equals 0 and here at x equals 3. 1, 2, 3. So that gives me a lot of information. So what I'm going to do, if I want to go and figure out my limits as it approaches 1, is I'm going to choose a number in here between 0 and 1. I just want to figure out if it's positive or negative, and you'll see why in a minute. And then as I approach it from this side, I'm going to choose a number between 1 and 3. So let's just choose a number between, let's choose 1/2. What happens if we do 1/2, right? Because I'm going to approach this vertical asymptote as from the left. So if I plug in 1/2, I think you guys would agree I get 1/2 squared minus 3 times 1/2 all over, 1/2 minus 1. I don't really care what that number is. I just care if it's positive or negative. So let's see. This is going to be 1/4 minus 3/2. So that top is going to be negative. And the bottom is going to be 1/2 minus 1. So that bottom is going to be negative. So it's a negative over a negative. So what this graph's going to actually look like, and see if this makes sense to you, there's an x-intercept here. It's positive here, so it's got to be hugging that. It's got to be hugging this asymptote like this. And then I don't know what's going on here. I'm just going to kind of make it go down like that. I just know it passes through the x-axis. So what does it tell me? It tells me that this thing is going to positive infinity. What about from the other side? Well, from the other side, I could plug in, 2. So what happens when I plug in 2? I get 2 squared minus 3 times 2 over 2 minus 1. Well, in the numerator, that's going to be 4 minus 6, which is a negative number. And in the denominator is 2 minus 1, which is a positive. So now this is negative, right? So in other words, what's going on here is this thing is doing this, okay? Again, I know that this number is negative. So any point in from here to here is negative. So this is going to neg infinity. So conclusion, this one is going to neg infinity. So if I wanted to make my overall conclusion, I would say limit does not exist for the entire function, but these are the descriptions as to what's going on. One more time, because I know there was a lot going on there. If you do not like making the graphs, I feel very comfortable making graphs. But if you don't feel comfortable making graphs, make a table. Okay? You did tables for 1.2. It's going to work exactly the same way, and it's very straightforward, okay? Let's move on. So we're going to look at some properties. We're going to look at some properties of limits, okay? So this is kind of poorly spaced. That's unfortunate. So maybe, actually, you know what? I see what happens. So give me a second here. I changed things around a little bit today when I was trying to get this ready for you guys. And now I see that this did not get moved properly. So why don't you guys pause the video right here, get this stuff down. Okay, the big things I want you guys to take from this, and this is good. I hope this makes sense to you, right? So we got some limit. F of x as we approach c is going to infinity. The other function is going to a number, right? So think of it, this is like 2, this is going to infinity. Well, think about what this means. If I'm going to add or subtract these limits, so this one's going to infinity, this is going to a number, right? Infinity plus a number is still infinity. Infinity minus a number is still infinity, right? So that should make sense to us. The same thing with the products, right? If I take infinity and I multiply it to, a number, but in this case, that number can't be 0 because, that's a problem. That's a future us problem. So as long as that, as long as that limit is positive, we're going to positive infinity. But the big key here is it's not 0. So that should make sense though, right? Infinity times 5 is still infinity. And then finally, this one is the interesting one, right? And we've seen this before, but I want to emphasize it to you because it is important. If the denominator is going to infinity, right? So this is like 7 and this is going to infinity. Well, think what's going on here, right? So let's just see what's going on. So Let's start at 7 over 1. Okay, so that's 7. Let's go to 7 over 10. Okay, that's a little less than 1. Let's go to 7 over 100, right? This denominator is growing and growing and growing. What's happening to this fraction, right? This fraction is getting closer and closer and closer to 0 because there's, as you guys know, well, as you've seen before, there's a horizontal asymptote there. So when the denominator is going to infinity like this, right? So we have a number over infinity, the whole thing's going to 0. Okay? Okay, let's play with some examples here. Let's see what we can do with these. So I'm gonna go through these with you. You know, obviously, if you want to pause the video and try some stuff on your own, you're more than welcome to. But I think I'll go through these with you. So let's see here. One of the things we know we can do with limits is we can break these up. So I'm going to take the limit. I could use some different properties here, but I'm just going to do this just to make sure that we're okay with this. So you guys are, you know, you're comfortable with this. So I'm going to do this. I'm breaking this up because we know we can do that. The first one, as you know, flashcard, this becomes 1. Notice this is going to 0. This isn't going to infinity. This is going to 0. We know there's a vertical asymptote here. We know that means it's going to infinity. In this case, because the denominator is always squared, it's going to positive infinity. If you're wondering why it's going to positive infinity, pause this video for a second. Ask yourself, why did I say positive infinity? Why did I say it was going to positive infinity and not negative infinity? How did I know that? The key, right, is the fact that it's squared. So, continuing, I think you guys would agree, 1 plus infinity is infinity. Now, you might say, hey, couldn't I have just, taken this sum and done, kind of done what they said to do here? And the answer is yes. I could look at it, the whole thing at one time. I think it is easier to kind of break these up. I like to break these up in visual using limit properties. So I took the limit of each of these, I broke them up instead of analyzing the whole thing at one point. So I'm going to do the same thing with each of these. So for example, and maybe you can do this right now, I'm going to take the limit of the numerator, figure out what that is. I'm going to take the limit of the denominator, figure out what that is, and then I'm going to look at that quotient put together. So let's see what we got. So I'm going to take the limit of the numerator. So the limit of the numerator is, so I think you guys would agree, x squared plus 1. If I were to plug in 1, looks like I would get 2. Okay, let's look at the limit of the denominator. Where am I going to go here? I'm going to go here. I think I need a little extra room. I'm going to turn that denominator into a fraction. So this is going to be cosine pi x over sine pi x. So let's see what's going on here. So as it approaches 1, this becomes cosine pi. Cosine pi is -1, right? But it's going to also be over sine pi. Sine pi is 0. So this is definitely going, this is going to either positive or negative infinity. Okay? So just to be clear, if we were to look at this, the numerator is going, that limit of the numerator is going to, what did I say? I said 2. Why did I say 2? It is going to, what is it? Cosine of pi is -1. The sine of pi is going to infinity. Now, in this case, it doesn't matter whether it's going to positive or negative infinity. I'll show you why in just a minute. But if you wanted to look at it, if you were like, is it going to positive or negative infinity? One of the things you could do is you can say, well, let's see. Here's my unit circle. I'm approaching pi from numbers that are less than pi. I think you guys would agree in this quadrant, sine's positive. So this is going to be going to positive infinity. So in this case, it's -1 divided by positive infinity. This is negative infinity. I want to emphasize, though, it's not going to matter. And here's why. Let's put the whole thing together. So in this case, when I take the limit as x approaches 1 of the top function divided by the limit as x approaches 1 from the bottom function, I'm just going to write it as this, right? What do we get? Well, this, we already know the top is going to go to 2. The bottom, again, it's going to go to positive infinity or negative infinity. It doesn't matter. It's going to some form of infinity. In this case, it was specifically going to negative infinity. But we know from this flashcard, when it's going to infinity, the whole thing goes to 0. Okay? It's going to 0. So one more time, because that one was a little bit harder. Let me just reiterate. The first thing I did is I said, what is the limit as x approaches 1 for this one? Oh, it is 2. Then I looked at the denominator, right? And I analyzed the denominator. And I knew it was going to some form of infinity. So a number divided by some form of infinity is 0. That's my conclusion. So it actually is a number, right? Let's look at this next one. This next one's kind of good because it's going to reiterate what we saw in B. So what I'd like you to do is just try it. Break cotangent up, see what you can do with it. Okay. So I'm going to catch up with you guys. First off, I'm going to pull that 3. It's a scalar. Let's just pull it out. So and I'm going to break cotangent x into, cosine x over sine x. Okay? So in this case, let's see what's going on here. We're approaching cotangent from, we're approaching 0 from the right. So again, let's think about what's going on here. If we were just to look at the limit as for the cosine function, if I were just going to look at the limit for the numerator, the limit as it approaches 0 of cosine x, well, we know the cosine of 0 is 1, so that works out nicely. From the denominator, this is the one that may give you a little difficulty. Okay? We know that at 0 there's a vertical, that sine of 0 is 0. So we know there's going to be a vertical asymptote. I think, well, let's just put 0 for right now. Let me put 0 for right now. There's not a vertical asymptote, but sine doesn't have vertical asymptotes. So kind of scratch that for a second. Let's now go put this whole thing together. So in this case, putting the whole thing together, we get the limit as x approaches 0 from the right of cosine x over the limit as x approaches 0 from the right of sine x. So in the numerator, we know it's going to 1. That's easy peasy. It's the bottom. Now the bottom's where you're going to struggle. We know that it's going to 0, so we know it's going to infinity or negative infinity. What I want you to figure out is which is it doing? Okay? So you can do that in one of two ways. You can approach 0 from the right. So you can choose numbers that are just slightly bigger than 0, right? So I can plug in 0.5, 0.25, 0.1, 0.01. See what's going on there. Or you can do it like I do, and you can say, okay, here's my unit circle. Here's 0, right? This is the thing it's going to 0. I'm approaching 0 from the right, so I'm approaching it from numbers that are bigger than 0. So it's kind of doing something like this. Is sine positive or negative in that quadrant? Right? Because no matter what I plug in, sine's going to stay, positive or negative. In this case, pausing for a second, you figure it out, but in this case, right, this is positive. Why? Because in quadrant 1, sine is positive. So let's see what we have here. Sorry, that's not infinity. This is 0. But in this case, right, let me pause for just a second. So, one more time, what's going on here is we have a vertical asymptote, and we note that we already know it's going to infinity. The only question was, is it going to positive infinity or negative infinity? Because sine is positive, this thing's got to be going to positive infinity. Okay, I know that was a little confusing. I apologize. I hope that makes sense to you. So let me just one more time. One thing you can do is you can make a table, right? If you're not comfortable, you can always make a table and see what's going on. There's a vertical asymptote there. You plug in numbers to the right. That's totally fine. In this case, what I chose to do is I said, I know the numerator is going to 1. I know the denominator is going to 0. So I know there's a vertical asymptote. I know that as I approach 0 from the right, I'm approaching it from quadrant 1. So sine is positive there. So this is going to positive infinity. Okay. Again, though, if you don't like that, please make a table. Okay. Let's look at this last one. Okay. Looking at this last one. So in this case, there isn't much to say here. I don't quite know why I included this one. So let's just see what's going to go on here. I'm going to break it up into 2 different pieces. Even that, I don't know. Like I said, there's just not much going on here. But let's do it. So in the first one, I think you guys would agree. The limit as x approaches 0 from the left of x squared is just 0. From this one, there's a vertical asymptote, right? There's definitely a vertical asymptote at 0. So the question is it positive infinity or negative infinity? This is for you. Okay, I want you guys to figure this out. Is this thing going to negative infinity or positive infinity? Well, let's look. This is approaching from the left-hand side. So for the x values, I'm approaching 0 from the left. So I'm only plugging in negative numbers. So this is going to negative infinity. If you are not comfortable, right? If you're like, I don't like that. This really is hard for me. It's a good skill, by the way. Just sitting there and thinking about it for a minute and imagining what's going on is such a huge, valuable skill. Okay? Instead of just kind of going, I'm going to go to this tool that I know how to use and I can turn my brain off, turn your brain on and think about it for just a little bit. But once you've kind of made your educated guess, if you then want to say, okay, I'm going to go and make a table for numbers that are less than 0, it's approaching 0 from the left of this function, and confirm that it's going to negative infinity, that's fine. Obviously, final conclusion, it's negative infinity, so our limit does not exist. Okay? Anyway, let me double check. Yep, that is it. That is this lesson. I hope to see you all on Monday.